I'm going to start the recording. So line integrals. Now, we learned in section 13.1 about vector fields. And we saw that vector fields can model a variety of real-world phenomena. For instance, a gravitational field can be modeled with a vector field. A velocity field can be modeled with a vector field. Electric force fields can be modeled with vector fields. And what we want to do, one key thing that we want to do with a vector field is if a particle moves in the vector field, what work does the vector field do in moving the particle from one point to another point in the vector field? And in order to do this kind of problem, we have to learn about something called line integrals. Line integrals. So I'm going to give you a guided tour here of section 13.2, and then we'll work an example out for the notes. But let's just kind of work through things carefully. So, okay, a particle moving in space. Okay, if you're talking in two dimensions, okay, a particle in space moving along some curve C would have parametric equations given by x of t and y of t. Okay, and we restrict our time to be between values of a and b. So what we want to do is we want to take a function, okay, of x and y and multiply it by delta s, which is the length of a subarc. So let me go here. Well, hold on here. All right, let me go here to this picture. So in figure 1, you have an arc. You have an arc C, a curve in space C, and it moves from a point P sub 0 to a point P sub n. Okay, so it has a starting point and an ending point. And the different points are functions of x and y. Okay, and in other words, I want to say this the right way. A point on the space curve has coordinates x and y. But the coordinates x and y are themselves functions of time t. So you see below you have an interval, a time interval going from A to B. And for instance, you have a point, you have there two arrows drawn to points P sub I minus 1 and point P sub I. Well, so between the times of T sub I minus 1 and T sub I, you have these points P sub I minus 1, and you have an arc going from P sub I minus 1 to P sub I. So what we want to do is we want to treat that little arc between the points P sub I minus 1 and P sub I as a delta S. In other words, it's a little sublength of arc. It's a little bit of arc length, delta S. Okay, so basically the curve C, which is one big long arc, can be broken up into a bunch of little individual arcs. And the little individual arcs are dependent on the time that the curve is at. So what if we were to take, okay, the function, so some function of two variables, okay, and what if we were to multiply the function of two variables for different coordinates multiply that by different delta S's, delta S sub i's. So the delta S sub I would be the ith arc corresponding to the coordinate x sub I, y sub I, but x sub I, y sub I would correspond to some time. Okay, that's it. I mean, it's sort of an interesting idea. Take a value of a function and multiply it by an arc, by a piece of an arc, the length of a little piece of an arc. It's an interesting idea. Okay, well, if we were to take the limit as n goes to infinity of this Riemann sum, okay, and that means you would sample more and more points along the curve C, okay, more time values. If we were to take the limit of that Riemann sum, we would get what's called a line integral. And it's a line integral of the function along the curve C. That's called your line integral. Okay, now it's a little abstract right now, but I think you agree that as n goes to infinity, delta S is going to become ds, and the Riemann sum becomes an integral. All right, are there any questions so far? All right, well, let's continue. So, all right, the thing is, we're not used to integrating with respect to arc length S. We're not used to that. We're used to integrating with respect, for instance, to time, t. And in fact, the functions x and y are functions, the points on the curve C are themselves functions of time. As time changes, the point changes. And all the different points trace out a curve C as time changes. So it would be nice if we could take this line integral of the function f along curve C and change the variable that we're integrating to, change it so it's with respect to t. Well, remember, I don't know, I mean, if you remember, in calculus 2, you learned that hold on here, did I lose the book here? Let me bring it back. I don't know how that happened. Hold on, class. Let me bring it back. Let me log out of WebAssign and just come back in. Sometimes I have to do that if WebAssign's open too long, I guess. Hang on. This will take just a minute. Okay. One moment. Okay, good. Let's get the ebook back. Okay, let's. Okay, so what are we going to do with ds? Well, think about delta s in that formula there, in that first formula, the line integral of the function along C. Okay, that line integral, delta s is an arc length, but how do we find the length of an arc? You learn that the length of our arc is an integral from a to b of the square root of the sum of the derivatives of x and y with respect to t squared. In other words, the length is the integral from a to b of the square root of the sum of dx dt squared plus dy dt squared. How many recall that formula, that section 6.4 formula in Calculus 2? Okay, Eric remembers it. Very good. All right. Well, so essentially what we can do is this. It's really this simple. Take the, and I'm constantly checking here. All right, take the ds, okay, and replace it with the square root of, we'll replace it with, I want to say this the right way. All right, hold on, class. If you were to take the derivative, okay, of the, one moment, hold on. Just give me a moment here. Okay, so do you see what they're doing there? Where they're replacing the ds with the square root of dx dt squared plus dy dt squared dt. Do you see how they're doing that? I mean, are we okay with that? So they want to go from an integral with, okay, thank you, Christian. They want to go to an integral with respect to s to an integral with respect to t. So of course, x and y, they note that x and y are functions of t. And ds dt, okay, if you want to say this the right way, they replace ds with that, with what you see there. Okay, they replace ds with what you see there. Let me check one thing, class. Hold on just a minute. I want to check just one thing before I move forward here. I want to just check one thing. Let me see here in my notes. I'm just checking one thing. And I want to just see if it's worth, kind of worth doing or not. So take a pause for a minute. Take a pause. All right, let's take this, let's accept this for now. And then I may want to go back and look at it again, but let's just move forward on this for now. So, okay. So, well, yeah, I mean, here's what they're doing actually. This is really what I was looking for. If s of t is the length of a curve C between one point given by the vector r of a and another point given by the vector r of t, then the derivative of ds dt would simply equal that square root that you see there. okay, by the fundamental theorem of calculus, right? And so therefore, ds would equal that square root of dx dt squared plus dy dt squared times dt. Okay, I'm feeling very comfortable. I mean, I should feel comfortable, right? But are you feeling comfortable with that? Are you feeling comfortable? I'm trying to help you feel comfortable with this formula above and why it's true. They're just using a different parameterization. And by the fact that ds dt equals the square root of dx dt squared plus dy dt squared, they can convert the line integral with respect to arc length x to the line integral with respect to variable t. Okay. Are there any questions on that? Who's feeling okay with that? Who's all right with that? All right, good, Ryan, good. Okay, all right. So, all right, Christian's good too. Excellent. So, what's really, geometrically, what are we finding here? What are we really finding with this line integral? It really resembles basically the area of a curtain. See here in figure 2? If you look here at that blue, you have a curve C, and you have a function, a surface above the curve C. The curve C is in the xy plane, and you have this function above it, a surface, a function of x and y. And if you were to take the value of the function at different points, okay, different coordinates, and multiply that by the little piece, like by the arc length at that coordinate, you would get the area of that curtain. Okay, so if your function is positive, then the line integral represents the area of a fence or a curtain in figure 2, whose base is curve C and whose height above the point is the function of x and y. Okay, now again, how's this going to relate to computing work? Well, we'll get there. But let's just, are there any questions moving forward here? Any questions right now? Okay, so integrating along a semicircle. Okay, so in this problem, they want you to evaluate this line integral where C is the upper half of the unit circle. Well, of course, if we're going to use the formula where we compute the line integral and we're using the parameter t, then naturally what we need to do is find what the curve C is, the parameterization. It says C is the upper half of the unit circle. Well, for a unit circle, you're used to, when you parameterize the unit circle, you're used to letting x equals cosine t and y equals sine of t. Okay, now let me ask you this. What would the limits be? What would the t limits be if we're talking the upper half of a unit circle? What would the t limits have to be? T is going to go from 0 to what? How do we get? So if t okay, so I saw an answer. If t goes from 0 to 2 pi, that traces out a whole circle. We want the top half of the circle, and that's right, Christian. T would go from 0 to pi. And I thank you for all responses. No problem. Eric, that's right. That's right. So, okay, well, then let's compute the line integral just by, hold on, let me go up here. Let's compute this line integral. So they work it out here. They work it out. So x is cosine of t and y is sine of t. So they replace 2 plus x squared y ds with 2 plus cosine squared of t sine of t. And then the ds is, right there. It's the square root of that function dt, square root of dx dt squared plus dy dt squared dt. And it turns out that the line integral of the function with respect to, no, hold on. The line integral of the function f along that curve C is equal to 2 pi plus 2 over 3. Okay? I mean, that you've computed a line integral. Okay, are there any questions on that? All right, well then let's move forward if we're good here. Okay, so all right, you can have a curve C that consists of the sum of curves. Okay, you can have a piecewise smooth curve, like here they show in figure 4. Okay, that's the sum of, in this case, 4 curves. So the line integral of a function along a curve C would be the sum of the line integrals along each of the smooth pieces of C. Okay, so when you have a different, if the curve consists of different, if it's a piecewise curve and the curve changes, then that changes the parameterization. So to compute the line integral across the entire curve means you have to compute the sum of the line integrals along each individual curve whose sum makes up the entire curve. Okay, so for instance, in example 1 or example 2, they want you to evaluate this line integral where C consists of the arc C1 of the parabola y equals x squared that goes from the origin to 1, 1, followed by the vertical line segment C2 that goes from 1, 1 to 2, 2. So this line integral is going to require us to add 2 line integrals. All right, and the figure here, they have a figure. I mean, this is what our curve C is. It's the sum of a parabola that goes from t equals 0. Well, it goes from x equals 0 to x equals 1, and then plus a line segment that goes from x equals 1 to well, y equals 1 to y equals 2. So now this is an interesting problem because you see the parameterization, you don't have to use parameter t. You can find a line integral with different parameterizations. So what they do is they say, okay, well, let's choose x as the parameter. Okay, let's choose x as the parameter. All we need to do is find a parameterization, like for this parabola that goes from 0, 0 to 1, 1. All we need to do is find a parameterization that traces out that parabola. Well, you could let x equals t and y equals t squared and let t go from 0 to 1. But you could also say, hey, I want x as my parameter. So I'll let x equals x, I'll let y equals x squared, and x goes from 0 to 1. That will trace out the same parabola. Okay, that'll trace out the same parabola. Right? And so when we compute the line integral using this parameterization, you see instead of dx dt and dy dt, they have dx dx and dy dx because x is your parameter. And they work it out, they leave out some steps. There should be a substitution here, but the line integral is going to be 5 times square root of 5 minus 1 divided by 6. Okay, are there any questions on that? Okay, well now let's look at the second line integral. So the second line, the second curve is that vertical line segment that goes from 1, 1 to 2, 2. So what they do is they say, okay, well, let's let y be the parameter. And it makes sense. Now we could let, for instance, hold on, I gotta go down here. Yeah, for the second curve, C2, okay, and remember, what is C2? C2 is this line segment that goes from 1, 1 to 2, 2. So what's changing is the y value, not the x value. So they say, okay, well, for that line segment, it's convenient to just let y be the parameter and let x equals 1, because x is always 1, and then let y vary between 1 and 2. Now we could have just as easily let x equals 1 and y equals t, and let t vary between 1 and 2. The parameterization, you don't have to always have the same parameter, to get the same curve. And they're choosing y as the parameter. I personally like to always choose t as my parameter. It's just my preference, but at any rate, that's no problem. So then what they do is they compute the line integral along that second curve, C2, and they get a 2. And so then the sum, the full line integral across that curve C would be equal to 5 root 5 minus 1 over 6 plus 2. That would be the full line integral. Okay. Okay, and they mention here in terms of an application, and I don't want to get too deep into physics, but if the mass of a wire, okay, hold on, let me just highlight this. They talk about the mass of a wire. If you were to take the density, if you have a density function and you multiply that by the arc length, then the mass of the wire would be a line integral. And if you have then the mass of the wire as this line integral, then the center of mass can be represented as the x bar and the y bar. You've seen center of mass before, but the line integrals are involved then in finding the centroid. Has anybody seen this maybe in one of their physics classes, these kind of formulas? I'm just kind of curious. All right, well, I just wanted to bring it to your attention because I know some of you are taking like physics 2 and 3. And they talk about an example where they find a center of a mass of a wire. But I'm going to just I'm going to just kind of move forward here. Okay, we don't want to get too deep into physics. I mean, we want to do things that are intuitive and then support physics here. So, okay, let's continue now. Okay, line integrals. We looked at a line integral. Okay, that was a line integral along. Hold on here. Hold on, class. Okay, I want to highlight that. Good, good. So we looked at a line integral of a function along a curve C with respect to S, with respect to arc length. But if you replace the S, if you're talking like, I want to say this the right way. If you have, instead of if you have like a horizontal arc, like a line segment going horizontally, then the arc length is the same. The delta S would be the same as delta X. If your arc is a horizontal, like it's a line segment basically, then delta S is the same as dx. And you can replace in the definition for the line integral, you can replace the ds with the dx, and it turns out that you're going to end up, well, the dy is going to equal 0 if it's a horizontal arc. Then you know there's no change in y for a horizontal arc, so dy equals 0, but and ds would equal dx. So what essentially happens is the square root of dx dt squared plus dy dt squared becomes the square root of dx dt squared, and that let me show you here. Let me show you on the whiteboard here. Okay, hang on. Let me show you here. So, one moment. So, okay. So here is the integral. Here. Oh, whoops. I don't want to touch that. Hold on. Sometimes it's better to use the mouse for erasing. Okay, so the integral from a to b, okay, of f of xt yt square root of dx dt squared plus dy dt squared dt. Now, what if ds were equal to dt? So this is the definition, okay, for the line integral. Now, if ds equals dt, okay, in other words, that would be like if your arc, I want to say this exactly the right way, that would be if your arc were, no, I'm sorry, I made one error here, hold on. Hold on, we're gonna get it. Oh, I gotta take this blasted thing off. All right, hang on, get this thing off. We're gonna get it. What I meant is if ds is equal to dx, okay, so that means like, you know, you go from, and I want to be careful here, you go from one point, okay, one point, got to be very careful. You go from one point and you end up at another point, and it's along a horizontal, just a horizontal line segment. Okay, then the integral of the contour, sorry, the line integral, if we replace ds with dx, that's going to get us the integral of a to b of, hold on here, okay, that's going to get us the line integral. Where, okay, so let's say this the right way. So I'm going to have dx dt squared, but then dy is 0. Okay, dy is equal to 0 because there's, for this horizontal line segment, this arc, that's a horizontal line segment, is there's movement in the x direction. Okay, there's a change in the x direction, but is there any change in the y direction? If you think about like coordinates on that line segment, there's no change in y. That's right, Ryan. And so that means then that dy is equal to 0. This implies dy would equal to 0 because the entire arc is horizontal. So what happens is then you're left here, I mean, this term here becomes 0, and you're left with the square root of, I didn't want that to go that far, hold on. Okay. Yeah, you're left with the square root of dx dt squared. What's the square root of dx dt squared, class? That's just dx dt. Good. Good, Ryan. Good, Eric. And so what's going to happen? What's going to happen to this dt and this dt here in the denominator? What's going to happen to them? They cancel out. They simplify out. And so when they simplify out, you got a 1 and a 1, and you just have a dx. Okay, so this whole thing, maybe I'll use the mouse here. This entire part of the integral just becomes dx. Are there any questions on that? All right. Well, okay, so now when we look in the book, when they mention about a line integral, they mention about line integrals with respect to x and y. Well, here's the line integral. Hold on. I'm not quite where I want to be. Hold on. Let me go down here. Yeah, this is what I want. So line integrals with respect to x and y. Okay, well, now, okay, how are they getting this? How are they getting the I mean, they're replacing the dx, okay, with x prime of t dt. Okay, so the line integral with respect to x is the integral over the curve C of f of xy dx. But they're replacing dx in this formula 7 with x prime of t dt. Okay, so why can they do that? Well, let me ask you this. What does, let me go back to the board here. What does dx dt equal? It equals x prime of t. So therefore, dx is just equal to x prime of t dt. And that's why they can say that the integral, the line integral of the function along the curve C with respect to x, that's why they can say it equals the integral from a to b of x of t, the function x of t, y of t. Okay, hold on. I will not have messy stuff. Okay. I will not have messy stuff. Let me write it again. Okay, so x of t, y of t. Okay, and then they replace the dx with x prime of t dt. And similarly, if you wanted the line integral, okay, if you wanted the line integral of a function along a curve C with respect to y, that's given like this. Okay. Are there any questions on that? Any questions? How many are comfortable so far? I mean, it's all right. Christopher's good. I mean, really, we've derived these results. Thank you, Christopher. Thank you, John. Thank you, Ryan. We've derived these results without too much difficulty. All right, we're doing all right. So, okay, now line integrals with respect to x and respect to y often occurred together in problems. So we go back to the book here. I mean, let's just continue. All right, so now we know, now we feel good with these two results. And again, it's preferable to have t as the parameter. If you have a particle moving in space, it moves in space with respect to time, you know, so it's always nice to have t as a parameter. Now, something interesting too is that the line integrals with respect to x and y often occur together. And so it's customary to abbreviate the sum of a line integral with respect to x and a sum of a line integral with respect to y as that notation that you see there. Okay, it's very common. Okay, very common to do that. Okay, so are there any questions at all so far? All right, well, let's just continue. Let's just continue here. So, okay, one thing to notice too, that if you need to parameterize a line segment, okay, maybe I'll highlight this. If you need to parameterize a line segment, okay, because these problems involve parameterization of the curves. So a line segment, a quick way to get a parameterization of any line segment is take 1 minus t, multiply it by, at the starting point, r sub 0, and then add t times the ending point, r sub 1, those two vectors. And t is between 0 and 1. That's a very nice way to get the parameterization of a line segment. Okay, so that's a formula that you want to keep in mind. Okay, so that being said, and it's not hard to prove that. Trying to think, did you see this formula? Maybe trying to recall if you saw this back earlier. I think you might have seen this formula. How does anybody recall this formula from earlier in the semester? Parameterization of a line segment. Okay, Eric recalls it. All right, good. Well, all right, well, let's look at an example here. Let's look at an example. So here, okay, what we want to do is we want to do the following. Okay, we have the sum of two line integrals. This integral, the way it's written, it's the sum of two line integrals. One integral is with respect to x, and the other integral is with respect to y. Okay, so let me just go back to the board here for a minute. So what that means here, okay, if you have in example 4, we'll go back to it, but if you have this, okay, what that means is it's the sum of two line integrals. The sum of two line integrals. The sum of these two line integrals. So this is just notation. This is notation for what you see on the right-hand side. Okay. Okay, so then let's go back to the problem. Okay, so they want you to find the sum of the two line integrals in two ways. Well, I want to know. They want you to find that the sum of those two line integrals along two different paths. So notice that in the figure 7, in figure 7 here below, you have a path C1 that goes from point -5, -3 to 0, 2. And you have a path C2 that goes from -5, -3 to 0, 2. But it goes along a different, it's a parabolic path. So would the line integrals for, so the starting point and ending point of both paths is the same. The starting and ending point of paths C1 and C2 are the same. But does that mean that the line integrals will be the same? And the answer is no. The answer is no. So for the first one, they're going to focus on the line segment. They're going to focus on the line segment. Well, all right, the line segment here starts at -5, -3, and ends at 0, 2. Okay, so if you are to use this formula here, okay, the r sub 0 vector is going to be -5, -3, and the r sub 1 vector is going to be 0, 2. And if you substitute that in that formula and compute the r of t vector, what you're going to end up with is this parameterization for that line segment. And notice t is between 0 and 1. So if you're going to use that then, if you're going to use that with that parameterization, the way you compute the line integral as you see below. The line integral across the contour or the curve C1, well, y is 5t minus 3 squared, and dx, well, dx dt equals 5, right? If x equals 5t minus 5, then dx dt equals 5. Hence, dx is 5 dt. Okay, so I'm focused here now. And similarly, if y equals 5t minus 3, then dy dt equals 5, and so dy is 5 dt. And you just compute the line integrals. You're really computing two separate line integrals and adding them together. That's essentially what you're doing. And you can do that since both line integrals have the same limits and they're with respect to t. And you end up getting -5/6. Okay, so let me pause for a minute and see if anybody has any questions on this. Okay. Okay. Well, if you're good, then let's do the next part. Okay, the next part of the problem says, okay, let's look at this second path. Okay, C equals C2. I don't know if I want to. Well, hold on. It kind of, sometimes it lets me do some things, sometimes it lets me do other things. But we're going to go on part B now of this example 4. C2 is the arc of that parabola. X equals 4 minus y squared. Now, looking at the figure here, there's the parabola C2. What would you let be the parameter? would you let y be the parameter, or for that curve C2 in figure 7, would you let y be the parameter, or would you let x be the parameter? What would be more convenient to let be the parameter? What do you think? So for curve C2, to parameterize that curve, what's more convenient choice for a parameter? The variable x or the variable y? Well, what's the independent variable? X equals 4 minus y squared. Is the independent variable the x or the y? What do you think? Well, based on the function, x is a function of y, right? X equals 4 minus y squared. That parabola for curve C2, x is a function of y. So it seems clear that we would want to let y be the parameter, okay, since x is a function of y. And if we do that, okay, then in part B, we'll let x equals 4 minus y squared, and y will just be itself. Okay, now, and y goes from -3 to 2. Now, incidentally, we could have let x equals 4 minus t squared and y equals t, and t goes from -3 to 2. That would have been okay too. You see, it's okay to let t be the parameter as well. I tend to like to always let t be my parameter, but you can let y be the parameter. And if you do this, okay, you end up getting what you see here for the sum of the line integrals. Okay, so let me see here. I'm just going to write the first part down just to, hold on. Okay, so, okay. I want you to understand why it is as it is. Okay, let me go to the whiteboard. Let me go to the whiteboard here. And let's go ahead and write this down. So x equals 4 minus y squared. Y equals y. This is for curve C2 from in figure 7 from example 4. Okay, so okay, so line integral here. Okay, so what I like to do is I like to split this up. I know it's notation on the left here, but I generally don't like a notation where I have an integral where inside I have two differentials. Okay, I mean, I understand why they're doing it, but I like to do what I'm comfortable with, right? And I know this is true. Okay, so, all right, now from up here, x equals 4 minus y squared. So dx dy then is just going to equal negative 2y. And this implies that dx equals negative 2y dy. So this integral here, I can replace dx with negative 2y dy. And the second integral, well, x is equal to 4 minus y squared. So I'm going to put 4 minus y squared. You see the parameter is y, right? So we want everything in terms of y. Okay, so then this is going to get you then what they had. What they had was this. Whoops, hold on. Yeah, what they had was this. You know, but to get there, I like doing, I mean, you got to know this, right? You got to know that. And, now I'm very comfortable with that. Okay, the key in math is comfort, right? To do well in math, you have to be comfortable with what you're doing. And are there any questions before we go back to the example? Was this, how many found, was this helpful? Was this helpful for some of you? Showing that? Okay. All right, John, excellent. Okay, well then, now we'll go back to the problem at hand. Okay, back to the problem at hand. And now they compute this line integral and they get 40 and 5/6. So along the first line, along the first path C1, okay, along the first path C1, whoops, that line integral was equal to negative 5/6. But along the second path, so along the line segment C1, the line integral was equal to negative 5/6. But along the second path C2, that parabola, the line integral there was 40 and 5/6. Okay, and so that's interesting. And they note here, this is really a lot of good stuff you're learning here. They note that you got different answers in part A and B in this example, different answers, right? Well, in general, the value, even though the two curves had the same endpoints, in general, the value of a line integral depends not just on the endpoints of the curve, but also on the path. However, there are conditions under which a line integral is independent of the path. Okay, there are situations where that happens. Okay, and we'll get into that next week. Okay, so, and that's desirable, right? But that's only under certain situations. Now, one thing they also mention here is that the answers in example 4 depend on the direction or orientation of the curve. So the starting point in example 4 was -5, -3, and so you see here in the example, okay, how the curve C1, you're starting at -5, -3, and then there's an arrow going in the direction to 0, 2. So you're going from -5, -3 to 0, 2. Similarly, you're doing the same thing for C, the path C2. That curve, you're also going from -5, -3 to 0, 2. Look at the arrows. That the way that the arrows indicate movement. Which way are you moving? Okay, on the path. So that's fine. That's fine. But they make a note here. They make a note here that, hold on here. They note here that the values of the line integral depend on the orientation or direction of the curve. Okay, so if -C1 denoted the line segment going the other direction from 0 to, starting at 0.02 to -5 and -3, then it turns out that your line integral is going to be 5, 6, which is opposite -5, 6. -5, 6 was the value of the line integral when you start at -5, -3 and go to the 0.02. If you go the other direction, you get the negative of that. Negative of -5, 6 is 5, 6. So the point is, in general, yeah, and in general, hold on here. I want to kind of highlight all of this. There's a lot of stuff here in section 13.2. In general, a given parameterization determines an orientation of the curve with positive direction corresponding to an increasing values of the parameter. Okay, are there any questions so far? Okay, well let's do a little bit more here, and then I'm gonna set you on a break here. But let's do a little bit more. So, all right. So we've looked at examples where our curves are in the XY plane. Our curves are in the XY plane, but you know, and particles, for instance, are moving along a curve in the XY plane. But particles also move in space, right? In three-dimensional space. So you can have a curve C that has components X, Y, and Z. And if you were to look at the line integrals for that, they're analogous to what you learned for a two-dimensional curve. Here's the formula for a line integral of a function along a curve C with respect to arc length, S. You see, they have a typo there, don't they? Hey, that should be a plus dz dt squared. My goodness. All right. They have a typo there when I highlight that. Interesting. All right. And they note then, of course, that you can have integrals with line integrals with respect to X, Y, and Z. And so the kind of work you do, the kind of problems you do are analogous to what you just learned with two dimensions. So for instance, if you had a line integral in space, okay, and let's say that C, hold on here, let's say that C is a helix. C, hold on. Yeah, C is a helix. You know a helix, right? Okay, well, you would just compute the line integral as such. I mean, it's really just computing using the definition of a line integral and working it out. Okay, that's what it is. And also, you can have problems, for instance, where you have they want you to compute the sum of 3 line integrals with respect to x, y, and z in example 6. So they have they do this along 2 line segments, and really the work involved, I'll let you look at example 6, but it's just an extension. I mean, the work involved, I'll just maybe, you know, I mean, there's the two curves, and I mean, the work involved is just analogous to what you saw before. So I want to just kind of, I think, stop there. If there, I'll let you look at example 6. I think you'll be fine. I want to do a little more in section 13.2, but I want to stop there for a moment and give you a little time to work. So are there any questions at all? Okay, let me stop the recording.